In this video, we're going to talk about acids and bases. These are your learning targets. Let's first start with some examples of acids and bases. Probably one of the first things that come to mind are cleaning products like bleach. Bleach is a base. Shampoo is a base. What's acidic? We have citric acid, right? Lemons, oranges. You might remember acetic acid, right? Vinegar. Here are some other examples. Hydrangea flowers. You might have seen these flowers around your neighborhood. Maybe you have it in your own backyard. Hydrangea flowers can vary in color. You might have seen them in purple, pink, white, or blue. Well, the colors will depend on the acidity of the soil. So if you know someone who likes to plant, you'll see them actually measure the pH of their soil because it can actually kill their plants or it can help their plants thrive. So they really want to know the pH of the soil. Ants release formic acid to alert the entire colony of danger. We've all heard of acid rain, and acid rain can destroy buildings and statues. We have acid in our foods and drinks. We use it to flavor it. Again, just going back to the lemons, we have citric acid, right? And then we have stomach acid to help us digest our food, and amino acids make up every organ in our body. Now let's take a look at the different properties of acids and bases. Acids are defined by their hydrogen ions, so they contain hydrogen ions. If you take a look at the examples that I put on your notes, you have examples like HCl, hydrochloric acid, HNO3, nitric acid, H2CO3, carbonic acid. What do these things have in common besides the word acid? If you look at the formula, they all begin with hydrogen. It's these hydrogen ions that define what an acid is. And another word for hydrogen ion that you might hear throughout the video or just see on these slides is protons. So hydrogen ions are also known as protons. Acids taste sour. They are corrosive to metals, so it reacts easily with metals. It has a low pH. If you remember back in biology, if you learned about the pH scale, it goes from 0 to 14. We'll talk about it again later on in this video. But acids have a pH that's less than 7. They become less acidic when mixed with bases. They turn blue litmus paper red. Now litmus paper, you might remember pH paper that also showed you different colors depending on what the pH level was. Litmus paper is just a simple test. So you have a blue litmus paper, you have a red litmus paper. If the blue paper turns red, then it's just a simple test to tell you that it's an acid. So litmus is just a type of dye. And then acids are also defined by being a proton donor. So they like to give away these hydrogen ions. Okay. Bases contain hydroxide ions. Hydroxide is OH minus 1. So if you take a look at your examples, you have NaOH, sodium hydroxide, you have CaOH2, calcium hydroxide. So what do all of these have in common? That they have OH, hydroxide in them, okay? They taste bitter, they're chalky, they're slippery, they have a high pH, so anything greater than 7, so 8 to 14. They become less basic when mixed with acids. They turn red litmus paper blue. So to help you remember that, you just think of basic blue, BB. Bases will turn the paper blue. To show you this, I'm going to pull up a simulation. So I'm using this PhET simulation to show you the different colors between an acid and a base. Now, this isn't completely accurate because this is actually a pH paper. So a pH paper shows you different colors depending on what the pH level is. But in terms of it turning red or blue, that's going to be the same. So if I have an acid, I'm going to dip this paper in, and you see that it turns like a red-pink color. That tells us that we are dealing with an acid. Now if I have a base and I dip this paper in, you see that it turns blue, and that, again, is just a simple test to tell us if we are dealing with an acid or a base. Bases are also defined as proton acceptors. So they like to take these hydrogen ions, right? So if you have an acid and a base, and we'll talk about that, this is a neutralization reaction. Acids like to give away the hydrogen ions, and bases like to take the hydrogen ions. And right in the middle of our pH scale, we have a pH of 7. And we know that pH of 7 is neutral. And the best example of something that's neutral is water. So here we have equal concentrations, concentration meaning molarity, okay? Equal concentrations of hydrogen and hydroxide. So next we're going to talk about the pH scale, and as I mentioned before, the pH scale is from 0 to 14. If a substance is reading a pH level of 0 to 2, then we consider that very acidic. So we have strong acids there. And then we have weaker acids, slightly acidic. Here we have neutral at pH of 7. And then anything above 7 is basic, right? So if it's a pH of 14, then we say that is very basic. That's probably a strong base. As opposed to like 8 to 10, it's slightly basic. It's probably a weaker base. So this scale is showing you different examples of substances that we have around the house, substances that we consume. So milk you see here is actually slightly acidic. Some of you guys might think that milk is a base, but it's not. So a lot of our acids, or a lot of our foods and drinks, are more acidic, okay? Blood is slightly basic. A lot of these are cleaning products or medicine, okay? Milk and magnesia is like a medicine that helps you go to the bathroom. Some other examples I'm gonna show you with this simulation. So this is showing you just different pH levels. So water, we have a pH of 7. Here's drain cleaner. Drain cleaner has a pH of 13. Hand soap is pH of 10. I'm trying to show you examples that we didn't see in the slide. Spit is slightly acidic, or slightly basic at 7.4. Chicken soup, pH of 5.8. Let's see, vomit, I'm sure you're curious, has a pH of 2. Now, pH is actually power of hydrogen. So pH, yes, it tells us, simply put, how acidic or how basic a substance is, but it's actually directly related to the number of hydrogen ions. It's directly related to the concentration of hydrogen ions in a substance. So here on this scale, and we'll talk about the bottom part in a little bit, but pH, we see our normal 0 to 14, and right above it, this is the hydrogen ions, the concentration of hydrogen ions. So the brackets is just another symbol to indicate concentration, so molarity, okay? So if we have the brackets, we just don't write the unit molarity. So here we see that when the pH is low, meaning more acidic, the hydrogen ion concentration is high, okay? Because remember when we talked about acids, right? Acids are known for their hydrogen ions. They contain hydrogen ions. So the more hydrogen ions they have, the more acidic the substance is going to be. As opposed to if you go all the way to the opposite side of the scale at pH of 14, which we know is very basic, we can see that the hydrogen ion concentration is very low. It's 10 to the negative 14. Now the mathematical relationship between pH and the concentration of hydrogen ion is this. pH is equal to the negative log of hydrogen ion concentration. pH is the negative of the base 10 logarithm of the concentration of hydrogen ions in solution. Now I know what you're thinking. Oh dear God, she's using log. We're going to use log somehow. I promise you it's going to be easier than that. And you guys also have your calculators. You guys, if you look at your TI calculators, you have your log button, right? That's what we're going to use, okay? And then on the other side, we have pOH. Now, if pH tells us the power of hydrogen, what do you think the pOH will tell us? Power of hydroxide, right? So if you look at this scale here, pOH is actually the complete opposite of pH, okay? And pOH is related to the concentration of hydroxide ions, all right? So if you take a look here, when pOH is 14, meaning it's very acidic, okay? your hydroxide ion concentration is very low. But in a very basic solution, we go to the opposite end. If the pOH is 0, it means that the hydroxide ion concentration is very high, and they're complete opposites. Now, it's not the scale that I want you to memorize, but here we have the other relationship. pOH is equal to the negative log of the hydroxide ion concentration. So we talked about two relationships. The first one is the relationship between pH and the concentration of hydrogen ions. The second relationship is pOH and the concentration of hydroxide ions. The last one is the relationship between pH and pOH. Now remember, I said that the pOH is completely opposite of pH, right? And you can see that in the scale. pH is going from 0 to 14. When pH is 0, pOH is 14. When pH is 2, pOH is 12. Well, the third relationship here is that pH plus pOH is equal to 14. Now the other thing I want you to notice before we move on to our practice problems is if you look at these numbers for the concentration, they are very, very small numbers, right? 10 to negative 6, 10 to negative 9, 10 to negative 14. These are really small numbers, okay? Now as we go throughout the practice problems, remember I'm using the formulas that you see up here on the top right of your screen. pH plus pOH is equal to 14. pH is equal to negative log of the hydrogen ion concentration. pOH is equal to negative log of the hydroxide ion concentration. Alright, number one, what is the pH of a 0.001 molar solution of hydrochloric acid? So I'm given the concentration and they want the pH. So I will use the pH equals negative log of the hydrogen ion concentration, and I'm going to go ahead and plug in 0.001 for the hydrogen ion concentration, and you can use your TI calculator. You have a log button. You probably used it in your algebra class, and you just do negative log, and then it'll open up parentheses, 0.001, close your parentheses, and you'll get a pH of 3. Now, there's actually an easier method that I'll talk about in number 2, where I won't even use the calculator. What is the pH of a 1 times 10 to the negative 4 molar solution of nitric acid? So again, I could use the formula and plug it in like this, and then I'll get an answer of 4. The thing is, I actually don't even need the calculator because all I have to do is look at my exponent right here, and the negative log of this entire number is simply my exponent number 4. And if we go back to number 1, it's the same thing. If I were to rewrite this number, then the decimal place would have to move 3 times, right? So if I were to rewrite this, I could write 1 times 10 to the negative 3rd power. Okay, kind of messy, but there my exponent 3 is my answer. pH is equal to 3. See, I didn't even need my calculator. Number 3, what is the pH of a solution if the pOH is 10? Well, I'm given the pOH and I'm trying to find the pH. Well, which formula would I use? I would simply use pH plus pOH is equal to 14. So I plug in my number and pH is equal to 4, right? All I have to do is 14 minus 10. Number 4, what is the pH and pOH of a 1 times 10 to the negative 8 molar solution of sodium hydroxide? Well, I'm given the concentration, right? Now, if I take you back to numbers 1 and 2, this is asking about the pH, and the solution that they gave me, both of these are acids, right? Well, what do you notice about this one in number 4? I'm given the concentration, but this is of a sodium hydroxide. This is of a base, right? And so, which formula do you think I'll use? pH is equal to negative log of hydrogen ion concentration, or POH is equal to negative log of hydroxide ion concentration? Well, because this is the concentration of a base, I need to actually use POH is equal to negative log of the hydroxide ion concentration, again because sodium hydroxide is a base, okay? And so this concentration tells me my hydroxide ion concentration, so I'm going to go ahead and plug that in. And again, you can use your calculator, but you don't have to, because if you do the negative log of this number, again, it's just that exponent number. So the POH is equal to 8. And so how do I get the pH? Right, I do pH plus POH is equal to 14. I plug in my number, my POH, and I get a pH of 6. Number 5. What is the hydrogen ion concentration of a solution with a pH of 6? Now, they're asking for the concentration, and I am given the pH. So I'm supposed to use this formula and plug it in somehow, right, to get my answer. Well, if I want the concentration, then I would rewrite this, because this is base of 10 logarithm, okay? So it would be 10 to the negative pH. So for this, do I even have to plug it in? No, because it's a whole number. So if it's a whole number, then it's simply 10 to the negative 6. Hydrogen ion concentration is equal to 1 times 10 to the negative 6 moles per liter. Now, in one of our previous videos, the solutions video, we talked about electrolytes and how solutions can be strong electrolytes or they can be non-electrolytes, and that all depends on dissociation. So again, dissociation means separation of ions. If there's 100% dissociation, 100% of separation of ions, solutions were strong electrolytes, and if there was no dissociation, then solutions were non-electrolytes. And one of the tests that we talked about was just a simple light bulb test, right? Strong electrolytes will light up a light bulb very strongly, and non-electrolytes won't light up the light bulb at all. And so for acids and bases, they can partially dissociate or they can completely dissociate to form ions, and it all depends on their strength. Strong acids and strong bases form strong electrolytes, so there is 100% dissociation. Some examples of strong acids include nitric acid, sulfuric acid, and hydrochloric acid. Strong bases include barium hydroxide and all group 1 hydroxides. So remember, group 1 is the first column on the periodic table. So for example, like sodium hydroxide and potassium hydroxide. And then there are weak acids and bases that form weak electrolytes because there's only partial dissociation. So there's only a little bit of separation into ions. So a couple examples of weak acids include carbonic acid and acetic acid, and a weak base is ammonia, NH3. So I'm going to show you this PhET simulation to show you what I mean by complete dissociation and partial dissociation of acids and bases. So for a strong acid, if you take a look here, the HA represents the strong acid, and it dissociates into A minus and H3O plus, which we can think of as H plus, okay? And so here on a molecular level, it shows you A minus and H plus here in the red, whereas if we were to compare this to a weak acid, you see that there isn't a lot of dissociation, right? You still see a lot of the original form of the acid here, and a little bit of blue and a little bit of red. So this is partial dissociation, partial separation of ions versus complete dissociation of ions, okay? Same thing for our strong bases and weak base, okay? So you can see the difference there, right? complete dissociation, partial dissociation. So what does this mean in terms of our simple test for strong electrolytes versus weak electrolytes? Well, if we have a strong base and we stick these electrodes in here, our light bulb lights up completely, whereas a weak base, you see how dim the light is? Okay, so that's the difference there. And the same thing, weak acid, dim light, strong acid, bright light. When it comes to acids and bases, one lab technique that we do is called a titration. A titration is the slow addition of one solution, for example an acid, where we know the concentration, to a known volume of another solution, like a base, where we don't know the concentration, until the acid and base reach neutralization. So do you remember when we talked about neutralization reaction way back in our reactions unit? A neutralization reaction is when an acid and base react and it produces an ionic compound in water. For example, we have magnesium hydroxide and hydrochloric acid. Well, magnesium hydroxide is our base, we have our hydrochloric acid, and when these two react, it will form an ionic compound, magnesium chloride, which we know is also known as a salt, and water. And for all neutralization reactions, this is what we get. We always get an ionic compound and water. Well, in a titration, we use an equipment called burette. And a burette is basically like an upside down graduated cylinder. Okay? So here, if you look at this picture, here's our burette. This is how we stop the solution from coming out. And then down here, we have our flask. Okay, so usually we put our base in our burette and we have our acid in our flask. We know the concentration and the volume of our base, and we know the volume of our acid, but we don't know the concentration of our acid, and that's what we want to figure out in a titration. So a graduated cylinder, if you think about it, it goes from 0 all the way up to 50, right? Or all the way up to 10 or 100. And that we already know how to read. A burette is the opposite. Burette, the 0 starts up here and it goes down to 50 here. Why it's like that? It's because the solution flows down, and so it's easier to read that if it's going down, all you have to do is read it basically backwards, in a sense. Okay, so if you look at this close up here, this is not reading like 40.7, right, like we're used to doing with the graduated cylinder. Instead, it's the opposite, because it increases as it goes down, so it's 39.123, 39.3, okay? Now I'm going to show you a video of a titration.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength, and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again the pH changes very little. The endpoint occurs at this middle point on the curve.
So in the video, you saw that the titration stopped when the solution turned pink, right? And so there are different indicators. So an indicator is added to an acidic solution to tell us when to stop our titration. So for example, for phenolphthalein, when you put phenolphthalein into an acidic solution, it's colorless. And once you get to what we call an endpoint, which I'll talk about next, it'll start changing color to pink. And that's basically when you want to stop your titration, because that's where you reach the end point. And again, I'll talk about that in a couple of seconds. If you go past that end point, then your pink color will just start to turn like hot pink or bright pink. And there are different indicators that we use. There's, for example, thymol blue, where it goes from yellow to blue. There's bromothymol blue, again, yellow to blue. Phenol red, which goes from yellow to red. And then there's methyl violet, that goes from yellow to violet. So as you can see, it changes based on the pH as well. Okay, so this is what a titration curve looks like. So you saw this in the video as well. On the Y we have pH, on the X we have the volume that's added. And here you see that this is our starting point, and this is, because it's low in the graph, it's telling you that we were starting with an acid, right? Because the pH is pretty low. And as we start to add a base, you see that the pH starts to increase and it shoots up because we passed this endpoint, and then it becomes basically more basic because now we've added more base. So at this point here, this is called the equivalence point. The end point in the titration is telling us when to stop our titration, so we're looking for the color change, which is called the end point. On the graph, this is called an equivalence point. And the equivalence point, by definition, is the point at which moles of hydrogen ions from the acid is equal to the moles of hydroxide ions from the base. This is the stoichiometric point of titration. So at this point right here, this is telling us that we need to add this much volume in order to neutralize our acid or base solution. This is the formula we would use after performing a titration. So the formula is MaVANH is equal to MbVbNOH. So the A's stand for acid. So this is molarity of the acid times volume of the acid times moles of hydrogen ions. And we'll go over how to find the moles of hydrogen ions in a little bit. On the other side, it's Mb, so this is all of base, molarity of the base, times volume of the base, times moles of hydroxide ions. So let's go over this NH and NOH before we get started with our problems and calculations. So here are some examples of acids and bases. And to figure out the moles of hydrogen or the moles of hydroxide, we are simply counting our hydrogens and hydroxides. So if we look at nitric acid, how many H's do you see? Or can we count? 1, right? So for NH, moles of hydrogen, we would say that there's only 1 mole of hydrogen. What about the bottom one, sulfuric acid? How many hydrogens do you see? 2, so that's 2 moles of hydrogen. What about the next one, carbonic acid? Right, 2 moles of hydrogen. Now let's take a look at our base. How many moles of hydroxide do you see? So remember, hydroxide is OH, so all of this together. Moles. How many moles of hydroxide do you see? There's 1 mole of hydroxide. There's just 1 count of hydroxide. What about the next one, barium hydroxide? How many OHs are there? There's 2, right? So that's 2 moles of hydroxide. And how about the last one, acetic acid? Acetic acid has how many moles of hydrogen? 1 mole of hydrogen, okay? Now that we got that figured out, let's go ahead and take a look at our practice problems. Number 1, 30 milliliters of 0.1 molar sodium hydroxide neutralize 25 milliliters of HCl. Determine the concentration of the acid. So the first thing we want to do is go ahead and split up our acid from the base. So I'm going to write HCl for our acid and sodium hydroxide for our base. And again, we're just using the formula up here. MAVANH is equal to MBVBNOH. Okay, so we want to look for these types of information from our problem, right? So let's start with the acid, hydrochloric. Here we have 25 milliliters of hydrochloric, and it says determine the concentration of the acid. So, do we know molarity of the acid? No, we don't. So I'm going to write M. Do we know volume of the acid? Yes, it's 25 milliliters. And then how many moles of hydrogen for NH? So again, remember, we're just looking at this formula here, and we're simply looking at the H right here. So how many H's are there? There's 1, so we write 1 mole. Now let's do the base. Now here is everything that we need for the base. Okay? So what is the molarity of the base? 0.1. What is the volume of the base? 30 milliliters. How many moles of hydroxide do we have in sodium hydroxide? Right here. 1 mole. So we're going to go ahead and solve for this. M in this case will be our x. Okay, so our x variable. So we have 25x is equal to 3. And divide that, 3 divided by 25, x is equal to 0.12 molarity, moles per liter. Number 2, how much of 0.5 molar nitric acid is needed to neutralize 25 milliliters of 0.05 molar calcium hydroxide solution? So again, go ahead and split up your acid and base, nitric acid and calcium hydroxide. Do we know the molarity of the acid? Yes, we do. It's 0.5. Do we know the volume of the acid? No, we don't. How many moles of hydrogen are there? If you look at this, there's just 1 mole. So now let's do everything of the base. Molarity of the base, 0.05. Volume of the base, 25. How many moles of hydroxide do we have here? We have 2 moles. So let's go ahead and solve, and x is equal to, remember x is V, so the volume is 5 milliliters. Example number 3. Go ahead and read it to yourself, and I want you to go ahead and pause the video and try it out yourself, and then when you're ready, go ahead and play the video. So for problem number 3, we want to go ahead and, again, split it up into acid and base. So we have sulfuric acid and calcium hydroxide. So for the acid, we have 2m for the concentration. We do not know the volume, and there's 2 moles of hydrogen, and that's equal to 1.5 molarity, moles per liter, for the base, 455 milliliters for the base, and there are 2 moles of hydroxide. So once you solve for that, we get a volume of 341 milliliters. And that's it for acids and bases.